So for our project, we decided to recreate a virtual version of the Enigma machine, which was a German-developed ciphertext encoder that was used by the German military at the end of World War I and through the end of World War II. And it provided a compact portable cipher encoder that combined both mechanical systems, like spinning rotors, and electrical subsystems, like electrical connections for sending signals. Every Enigma machine consisted of 3 rotors that were interchangeable and had all 26 letters of the alphabet in a circular pattern. And every time a key was pressed on the Enigma machine, the first rotor would increment by 1 step, and the consecutive second and third rotors would increment by some other preset value. And every time a key was pressed, the signal would go through each of the 3 rotors, and after it passed through the third rotor, it would be reversed and sent backwards through the 3 rotors again, providing additional levels of encryption. Another component of the Enigma machine was the plugboard connections that were on the front of the machine, and it allowed 2 letters to be connected electrically. And so, for example, if on this image here, the F letter is connected to the J letter, if an F was pressed on the keyboard, the machine would interpret it as a J being pressed, and this provided yet another level of encryption. So this shows the complete machine with the plugboard connections on the front, the rotors on the top, and the keypad on the bottom of the top panel. So every time a key was pressed, the signal would go through the rotors, through the plugboard, and the encrypted letter would light up. And so for a message to be encrypted, it would be typed out on the keypad, and the corresponding letters that light up would be the encrypted message.
Alright, so as Max was saying, we have our enigma.cpp file, which is the main part of our entire program. In the beginning, we start by getting the connections to our plugboard, which is shown in our connections.cpp. This file reads in a setup.txt file, which will get the connections for us so that we can see which 2 letters are connected electronically. If there is, after we get the connections, we then also check to see if there are any errors inside of it, which is this here. If there are any errors, we will return some sort of error message to the user to tell them there's been a misconfiguration. For example, if A goes to A, then that's a problem. Or if A goes to B and A also goes to C, then that would also cause an error. Continuing on, we then want to set up our rotors for inside of the machine. That calls our setup rotors function, which is right here. That also reads the setup.txt file and gets the flags that we have for each rotor, and also gets their value and assigns it to our rotor positions, and also which rotor wants to be inserted. We want to be inserted into the machine. We'll get assigned to rotor option. We also then check to make sure that our rotors are assigned correctly and that there's no incorrect formatting inside of our setup.txt. Inside of the verify, we make sure that we're not using the same rotor more than once, and we also want to make sure that the index for each rotor is less than equal to 4. This is also our get flag function. This is what reads in our setup.txt file exactly. We check to see if there's a comment by seeing if the first 2 elements of the line are slashes, and if they are, then we just want to ignore it. Continuing on, making sure that the connections were safe. If not, like I said, we wanted to return the error message. If they are, we then collect an input from the user if it is not already predefined by one of our flags. We then want to go through each letter of the input and translate that into its designated connection. So if we get an A, we want to change that to a B. We then send that B into our rotors, which will return a different value, which we can see here through rotors. We have a string to int so that regardless of whether we type in a capital or lowercase, we will return the value that we want. We also have our rotors function, which goes through and sends them in through the right rotor and then goes to the end, reverses to the opposite side of that end rotor, and goes back through the opposite direction. Here is our exact encryption, so we can see starting at the right, splitting, going to the opposite side, and then coming back through the left. Each time we also want to increment our rotors, so we return the rightmost rotor one position each time. Once that hits the last key, we then will also increment the second one, and so on with the third. Here's our encryption. These are 5 predetermined rotors. We got this information off of Wikipedia. And then here we decide if it is forwards or backwards. If it's backwards, we have to do a little bit of additional math because it's not as easy as just simply adding 1 to offset for its turned position. But if it's going through it forwards, which means starting on the right and going left, we don't have too many problems. After that, we return the encrypted value back to Enigma, and then we plug that encrypted value back into the plug board, which will return our last layer of encryption, which we see out to the end user. Thanks.